Hello guys, today in this video I'm going to make you learn how to implement the multiplexer using the different operations just like the gate level implementation, case implementation, and the ternary operator implementations. So first I'm going to implement this multiplexer with the gate level implementation. Here is the code for the multiplexer and module, and just name it as you have named your file as DEMUX, so I will name it as DEMUX. So there are the total number of outputs and the inputs, and the output will be only out. The structure for the DEMUX is this one. Here you can see that there is only one put and two selection lines and the four inputs. So depending upon the selection we will obtain the inputs. Means that if I am going to apply the control 1 and control 2, so there will be if there is 1 1, so the value for higher bit value means that more significant bit will arrive at the output for it, and after that we are going to apply 0 0, then the least significant bit will be appeared at the output. So here is the algorithm for multiplexer. So there are four inputs: IN1, IN2, IN3 and IN4, and the control 1 and control 2 lines that are connected to the AND gate, and one are the simple line that will arrive at the two gates, and the two lines will arrive at not control 1 and not control 2, and there is only one output, and the four outputs are originating from the AND gate that are named as X, Y and ZW. So here we will see that these are the inputs: IN1, IN2, IN3 and control 1 and control 1 2. So the wire will be consisted of the inputs that are the gates are receiving. For example, the NOT gate is providing us these wires that I've shown. You can also don't write the code here because this doesn't make any difference in the code and the simulation as well. So here is the wire that is not control 2. Actually these wires are the output wires that are originating from the gates. Not control 1 is the wire that is the output wire of the NOT gate 1, and then this is the wire is the NOT gate 2 output, and these are the AND gate output wires. So here is the NOT operation applying these both two, means that the first is the output and the second is the input. So here is the second NOT gate, which is the has the output wire not control, and the second input wire is or the input probe is not control 1 2. Here you will see that the NOT operation will be performed when control 1 wire will be inserted, and then the not control 1 will be the outside or the output wire of this gate. So here you will see that this is the NOT operation, and first we this is the algorithm to write the code. So here you can see that the output wires are already or the output terminals are always written at the first value of this AND operation or the AND function. So W, X, Y and Z are the outputs of these gates. So the inputs of first AND gate will be the IN1, not control 1 and not control 1 2. Here you will see that the first input gate has the IN1 input, and then you will see that this Y is coming from not control 1, and then the second Y is coming from not control 2. So this is the NOT gate input, and the second is the NOT gate second AND gate input whose output is X, and IN2 IN not control 1 1 and control 1 2 respectively. Or secondly you will see that the OR gate has all the inputs that will be provided by the outputs of the 4 AND gate, and here is the out of the output terminal of the OR gate. So here is the you can see that the 4 terminal OR gate is attached, and the output of the OR gate is this, and W, X, Y and Z are the 4 inputs of the OR gate that we have applied this operation. So let's simulate it. Actually I've already simulated it. So first you have to provide this time clock with the value of let's start with this. We will provide a time clock of 100, and then we will provide the time clock here for 200, and then we will start from 50 to 6.25, means that the 50 will be applied at here, and then the half of 50 will be 25, and 25 time clock will be provided at here. You can see that this doesn't make any change. here is 25, and then the half of 25 is 12.5, and then again 6.25 time clock is provided, which is the half of the 12.5, means that 6.25. so then clicking OK. So running the functional simulation, you will see that the graph like this will be appeared. So it's just showing that the multiplexer is repeating the value after each successive waveform. So this is working properly, and the Rtl view for this multiplexer is this. You can see that the control inputs are attached, and the input 1, input 2, input 3 and input 4 is coming inside the AND gates, and then these AND gates are attached with the OR gates, and then the output is given. So this was a multiplexer that I used well, you can say the gate level implementation, and next we will use the. So here is the second method for the implementation of the multiplexer by using the logic statement implementation. So here we will see that I have renamed the module as DEMUX, and then the total number of the inputs and the outputs. The output will be only 1, and the inputs will be IN1, IN2, IN3, IN4, and control 1 and control 2. So these are the total input nodes. So you can easily assign only in one equation by using this. You can see that the AND operation is performed by this in IN1 control 1 with having its complement, and control 2 also is coming with this complement form. Let's see towards the figure. You can see that the output W has IN1 and complement of control 1, and then the complement of control 2 that is coming in the first AND gate. So here you can see that the first AND gate is this, whose all the inputs are having an AND operation with each other, and then OR operation with the next AND gate. And here you can see that the AND gates are then connected with the OR gates. So here we will see that the OR operation with the respective AND gates is applied. So let's start the simulation. Here I have already simulated. So go to the University VWF program and then click OK. So in order to obtain the waveform in here, we will see that click on the node finder, and then click on the list, and then you can shift all the inputs. So in order to shift these inputs to the graph, we will double click and then OK, and then OK. So you can see that only one output, and the total of 6 inputs will be appeared here, and then we have to set its time as we have set in the previous one. So here you can see that I will give it 100 time. So this is the 1010 and waveform is appearing, and then I will give it the 200 time period. So you will see that, and then again I will give the time period. Let's suppose I will give 50. So here you will start a countdown of 2 raised to power from here, because the fourth logic states are generally appeared in the form where the 000s and 11s appear in the two multiplication forms. So here I have applied already 50, so the half of the 50 is 25. So I will give the 25 period here, and then the half of 25 is 12, and then I will give 12.5, that is half of 25, and again the half of 12.5 is 6.25. So here the 6.25 comes. So now I will simulate the run the functional simulation. Here you will see that I'm going to apply. So now you will see that this will take a little bit time, and it will be compiled successfully. So let's see here what's happened. So you can see that it has successfully compiled, and it is showing the waveform as in the previous that I've implemented DEMUX. So here we can see that this equation has been proved, and then we will again locate its node in Rtl viewer, and then click yes. So you can see that all the combinations are same as in the previous circuit, because here is the OR gate that outputs the outputs of these 4 AND gates are attached with the input of the OR gate, and then these are the 6 inputs, that is input 1, 2, 3, 4, and control 1, control 2. Here is the third method for the implementation of the case statement. This case statement generally works as a switch statement as in C++ programming. Here you will see that when we insert the particular 2-bit value in the case statement, if the particular value matches any of these 4 statements, then any of these 4 statements then that value will be executed. For example, if I am going to insert 0 1, then the 0 will appear here and 1. So it will compare the values 0 1, that is a 2-bit value lying here. The output will be I and 2, means that the output value of input will be appeared at the output. And the second thing here is the always at the rate of this statement. And this statement is generally read as always add the changing in or 1 in 4 or whatever you say. It is clear that what is going on. This is the construct. This is the construct containing the statement which are only executing when any of the variables of the list variable change. The list of variable is called the sensitive list, sensitive list, whatever you say, because this construct is sensitive to their change and the keyword are always expected or whatever. So this is the case sensitive statement. If any of the integer that we have inserted despite of the other ones, so this statement will be executed because these sensitive values have been stored in case sensitivity. So this is the code for case sensitive implementation. So we will again go to the university VWF program, and then we will go to the graph. So I have already made the graph here, and then I am going to implement this graph using by clicking there, and then it will take a little bit time. So let's wait for a while in order to compile it. So here you see that it has successfully compiled, and you will see that it is giving us the perfect values that we are expecting as in the previous circuit. So this has successfully did the job that we were expecting. So we will go towards the Rtl view to see that what is the construction of the circuit that we have produced through the code. So you can see that it is the implementation of the MUX. Generally the MUX diagram is like this. It is the 4x1 MUX because the 4 inputs are taking and only the 1 output is going outside. And these 2 controls are the data, and these are the control statements for the data because these are only 1 and 0, means that these are 2-bit values and these are 4-bit values that we will apply at the input. So this will be at the output according to the situation that we were going to apply. Here we go to the example number 1, in which we assign the DEMUX using the assign operators, assign statements, or whatever we say. So this is the logic for the assign statements. We generally assign the values that are 3-bit values or 2-bit value, 4-bit value. So here we will see that I have renamed the file according to the previous ones. So this is the step that should be ignored. So next there are 2 inputs, that is select and that is D. You can also declare the input as a single statement but putting the comma in the here after select, and then again write the 3-bit 4-bit value for D. So I have separately do this to make nothing difference. So here the input is the 2-bit value, means that the selection lines the 2-bit value means it will be whether 0 0 0 1 1 0 or 1 1, and the output is Q, and the input D is a 4-bit value that will be provided to the 4 different inputs. So here is the wire Q. It is not necessary to put the wire. I was generally used here the wire, so you should not put here, or you can put it depending upon the situation, but I will use because it is originating from the ANDing terminals of the AND gate of the MUX that we generally use in the internal circuitry. So the wire is 1 0, and this is generally done by the selection lines, and then after that you will see that the D is also connected with the wire. So all these I have denoted with the wire. You can also neglect these all 3 lines and direct assign the Q value with deselect. So here is the most important parameter that I have assigned the value and declared a function in the function. Here you can see that D of square bracket is the function that is the input 3-bit 4-bit value, and then I have used the select command that is also the input we will take from the waveform. So here you can see that the 2-bit input will be inserted here, and then the D will be executed depending upon the
input that is saved in D, and then it will assign to Q. So here let's simulate it, and then we will see that here the graph like this will be appeared when we go to the edit node, insert, and then all this stuff like I previously did. The only different thing that you have to do is to just click these arrows, and then after that assign the particular values to the node. Let's suppose I have assigned to the selection lines. The one was of 200, and the other was of the time period 100. So here we go, and next we will apply the value here 50, here 25, and then the half is 12.5, and then again the half of 12.5 is 6.25. So here we're going to simulate it, and then we see what's the graph in the output waveform. So it takes a little bit time to compile. So here we go. Here you can see that here the waveform that we are seeing at the fourth last row, that is Q. So here you can see that the waveform is appearing as in the previous graph that we have seen. So the MUX is working as our expectations that we have previously defined. So it is working properly. So here is the Rtl view for this MUX. As you already know that the symbol for the MUX is this, and these are the selection lines of 2-bit values that we have given to that, and there are the 4-bit values that we have given to it, and then only one output, means that it is a 4x1 MUX. So here is the example number 2 using we will perform the multiplexer operation using the always block. Always block is already discussed previously that it uses the add the rate of and always, and I've already told you that the D or select are saved in the sensitive list, and then if only one of the command is insert using input, then it will give you the output, means that by the insertion of only one input it will execute the output. So this is the same as the previous example. Here you can see that the select wires or such things like that, but we have not assigned value. Instead we have just show here, means that in the previous code that I have written that ASSIGN, and then we assign the value to the Q, which is equals to the D is select. But here we only use the always command D or select, means that the selected, the value that we have take as an input, means that it is the simple variable or 2-bit number that we have declared as an input value. So it will save in D automatically instead of assigning the value to the Q. So here we are going to execute this code, and the output like this will be appeared. I have already started the simulation, and in order to save your time. So here you will see that this is the output of the DEMUX, and you will see that this is the wave as we were expected from the previous graphs. So this is the waveform, and this is the MUX symbol, which is generally shown in the Rtl view. This is the selection, and this is the selection, and this is the data lines of 4-bit value and only one output, means that it is 4x1 MUX. So here is example number 3. We will use the if statement for this implementation of MUX. Generally this is the same as the above code, and the wires are also same as above. This is always all this statement is same as above, but the only difference here will be the begin. Means that we are going to begin the statement that will start with if, and this will take a decision and check that if the select is 0, means that it is necessary it should be 0, then this will print Q is equals to D, and D of 0 means that the input that we have inserted first. So according to the situations, all these statements will hold. Generally one is 0 1, and this is 1 0 and this is 1 1. All these 4 combinations for the 2 bits. So this will select according to the situation, just depending upon what is chosen or what is executed. So this was the output waveform. For this I have already simulated it, and here you can see that the same wave is appearing at the output when we are applying the 200 nanoseconds, 100 nanoseconds, and then 50, 12, 25, 12.5, and 6.25. So these are showing that the DMUX is working properly, and it is the correct multiplexer is working properly. And here is the Rtl view for this, and this is these are the all the if statements that whether it will check that it is equal to 0, 3, 2, or 1. So depending on the situations, it will follow and execute the exact statement that we are going to. So here we go towards the example number 4 by using the conditional operator. These are the operators that check the conditions whether it is true or false, and when it is true, so it executes the statement that is written right after the question mark sign. So same is the concept of the ternary operators in C++ programming, but here we will use only this type of operation. We are going to assign Q the value of 4 gates. Here you can see that sorry, these are not AND gates, but these are only the 4 selections that we will perform. Here you can see that select 0. If this statement will be correct, then D0 will be equals to Q, and then if this statement will be correct, then D1 will be means that if select is equals to 1, then the output at D1 will be equals to Q, means that the second bit value will be appeared at the output, means the second input will be appeared at the output. But if this statement is wrong, it will again go towards the next statement. Here it will compare that it whether the inserted select value is 2. So whether and it will check. So if this is also wrong, then move on towards the next statement. So here I have not used select equals to 3 because it will already move to this equation and print there if 0, 1, or 2 are not equivalent to the select value. So this will print the output. So here we go towards again same process will be repeated like that, and then insert node, and then again node finder, then list, click the double arrow, and then OK. So here we go. Let's take you at the bottom of the value. So in order to observe the values, here we will put 50. Then again, sorry, I pressed the wrong button. So we will put here 25. That is the half of 50, and then the half of 25 will be 12.5, 12.5, and then there will be 6.25. That is the half of 12.5. So we will put here the time period of 200, and then here the time period of 100 will be appeared here. So in order to simulate it, and then clicking yes and saving the waveform, you will see that it will take a little bit time to be compiled. Let's wait 10 seconds. So here you can see that the same output waveform is appearing as we were expecting from this DMUX. Sorry, multiplexer. You can repeat DMUX. I don't know what's happening with me. So from this multiplexer, you will see that the same output waveform is appearing, and then if we see the Rtl view, here you can see that this is the Rtl view for this multiplexer. Now we will move on towards the DMUX exercise. So here we move on towards the gate level implementation of the DMUX. So it is the demultiplexer who has outputs of output 1, output 2, output 3, output 4, and 1 input. Generally, the demultiplexer is the circuit that contains 1 input and the 4 outputs. It is the 1x4 demultiplexer. So it has the 2 control knobs, or what you can say enabler, or such things like that. So here are the outputs that I have declared here, and then the input will be I and 1 that we will apply as the DMUX, and then there comes the control, and then control 2. So the wire is the NOT control. It is generally the NOT of, means that it is the negative of the control 1, and this NOT control 2 is the negative of control 2. So NOT gate will perform the operation because it is taking NOT control as an input. Sorry, here is the output, and then control as an input. So the wire, it will take control 2 as an input, and then it will give control 2 as output. And then we will see that the output 3, output 4, output 1 and output 2 are declared here. And then the input will be provided by IN1, 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 IN1 will be remain same because there is only one input, and the play of control 1 and control 1, not control 1 and control 2 will be taken. Here we will see the general example for the DMUX circuit. So here it will be easier to understand how these equations are performing. Uh, so here we will see the general circuit for demultiplexer. Here you can see that F is the only one input that is taken from the input side, and as a result 4 outputs are given by the demultiplexer. So here are the A and B. These have only the pure A. They are reaching here these two AND gates, and then there comes the NOT of A and NOT of B operation, which is generally known as control A and control B, and not control A and not control B, or not control 1 and not control 2 respectively, as we did in this. So here we will see only the AND gate A, which is performing the operation. So we will see, and let's compare it with the given code. Here we will see that the first AND gate is the output 4, and then input 1, and then control 1 and control 1. So here we will see that the input output is generally A. So we have declared that their output 4, and then it is taking the pure input, that is input 1. So these 4 inputs are going to the AND gate, and then here comes the NOT gate, sorry, A and B, that is purely coming towards the first AND gate. So here we see that all these gates are connected in such a way that it is fulfilling the complete diagram. So these are this is the code for this, and we will see here the output waveform. There is only one input that I have applied the 50 period, and then there applied I applied the 200, and here the 100, that is the half of 200. So there are 4 outputs. You can see that that are arranged in such a way. Then you see that the peak at the output 1 is coming only when the input 1 is at one logic state, while the other input in this entire cycle are 0. So when this cycle comes, you can see that only the control node A is open and the B is closed. So here you can see that this is the entire criteria for developing a DMUX through the code, and here is the entire diagram for DMUX. You can see that there are 4 outputs, 1 input and 2 control nodes. So here we will implement a logic statement in which the module is same as the previous one. So output, input and the wire is same as the previous ones. So the change in this code is just we are going to assign the values to the different outputs. Here we will see that the input 1, input these will be same, and here you can see that input and control 1 and control 2, these 3 terms are collectively making an AND gate, means that all the terms that are giving as an input to the AND gate will be equal to the output of this Cout1. So here we will see that control 1, control 1, control 1 is appearing here, and control 1, control 2 is appearing here. But the difference here is this is only in pure form, but this is in pure and this is in negation. This is in negation and this is in pure form, and this both are in negation, means that it is producing like a 0 0 0 1 1 0 and 1 1 arrangement. So this is the code for DMUX. So we will implement that. It will take a little bit time. So here it is experiment that we were expecting. Now come towards the Rtl view. Here is the Rtl view for this circuit. It will take a little bit time. So you can see that this is the Rtl view for this circuit. Here. So here we go towards the logical statement. Here is the expression for the DMUX that we already discussed. Then the change here is the assignment of the C out values. Here you can see that it is C out 4, C out 3, C out 2 and C out 1. Then the input ones are all same because it is only one input is applied, and the control 1, control 1, 2 and control 1, 1, 1, 2, and these are all forming the operations with the AND gate. This is actually the logical AND operation on these three terms. So you can see that after successful compilation, you should just adjust the value of 50 here, and then here you will give 200 and then 100 value given. So after the successful compilation, you can see that the waveform like the previous one is appearing, and this is the proof that the DMUX is working properly. And the next one you see that it has one input and the two control knobs, and then the DMUX is attaching with this one, and you can see that this is a satisfied circuit as we were expecting. So here is the last experiment for today. This is the if statement. These are the same thing that are written, but we have defined here the bits because here is the input value of 2-bit, and that is used for selection, because you know that the selection are two lines that are connected with the DMUX. So here is the input, only one bit value, so no need to define here the bits. And then the output value is X, means that it is a 4-bit, and we have registered this value in the X. And then the wire is connected with the select, and there is a wire in. You can also write this code or no. And here is the other statement which is used for select and in, and then there the if statement follows. If it will check that whether this statement is true, so the particular block of that statement will be executed. Or if that statement is not true, so it will shift towards the second statement, so it will check 1, so it is 1, so it will be executed, or 2, it will be executed. So depending on the situation, only one statement will be executed at a time. So here I have executed already this. So after successful compilation and giving the time to this 50 and then 200 and then 100 periods, you will see that the DMUX is giving us the output like this. And here you can see that this is like the previous value that we were expecting, no matter the wave shift here left or right, but you can see that the behavior of this output is same as the previous ones. So here is the Rtl view for this. You can see that the gate node in Rtl view will appear after a short period of time. So here is the output. Let's wait and see. So this is the last output for this. Now that you really enjoyed this lecture, so if you really like this video, please don't forget to subscribe, share and like my channel.